All right, good afternoon, y'all. So today I'm going to be going over enthalpy, specifically Thermochem and Hess's law. So let's just get started with enthalpy, specifically delta H or change in enthalpy. And this is basically how we're going to take a measure of energy per mole of a substance. And we have a couple enthalpies we can measure. By the way, we do this all in kilojoules per mole or kilojoule mole -1 if you're looking at a DP book. So with that, one thing I want to also quickly talk about is that this is what we call a state function. And what that means is that it only really matters where you start and end. All the middle parts don't matter at all. So if I take like some bottle of water or something and I heat it with fire, then I freeze it with some ice, and then I let it go to room temperature. And let's say it started at 298 Kelvin, which is room temperature, and it ends at 298 Kelvin. If we took the change in temperature, it would be zero. Much like enthalpy, it's a state function. All this middle stuff doesn't really matter at all. All that matters is the starting point and the ending point, and that's it. And that's what Hess's law is based off of. Hess's law basically says that if we have some reactant and some product, that there will be some change in enthalpy that exists between our reactants and our products. It might go up, it might go down. Honestly, who cares? But that's just what it is. Now, if we take our reactant and we make some intermediate, then we make maybe another intermediate, and then we go back up to the product, guess what? This delta H1, delta H2, delta H3, well, they all add up to delta H. We'll say delta H of F, delta H formation, will be equal to our delta H1 plus our delta H2 plus our delta H3. And we can do some fun problems with this. And what I want to do here is just jump into one slightly more difficult problem. I kind of want to dive into the deep end, and then we'll break it up into its subsequent parts. As we do this, we're going to be touching a bit on the enthalpy of formation, delta HF. So this is going to be enthalpy of formation. And our enthalpy of formation is basically the energy required to make 1 mole of a substance, to form that, to take those bonds and build them. Which remember, bond building is usually negative because it's going to be exothermic. So let's just go ahead and jump into our first and most complex problem. It automatically looks really hard. Basically, we're taking kind of a more complicated approach at this kind of reactant to product. What we have here is ethanol plus some oxygen. And to take ethanol, we can always burn it and make some products, carbon dioxide and water. Now we can also make ethanol using some intermediates. So we can take carbon and oxygen to make methanol, but that carbon and oxygen plus some hydrogen and oxygen can also go ahead and make water. When breaking up a problem like this, I find it really important to kind of just direct myself to only look at the arrows because that's kind of really the only important part to build this. So we have these 4 arrows here. We have 3 distinct sections. We have this, and you'll notice a plus sign. So this is actually one discrete section. Now you'll notice a couple other labels. This is delta H comb, which usually means the enthalpy of combustion. So this is something that we'll work with, and we'll actually be provided, I'll provide you with the delta H of combustion in this problem, 1,367 kilojoules per mole. Furthermore, we have some values here. We have our delta H of formation of water and our delta H of formation of carbon dioxide. These are well-known values that we can look up in a data book that we can look up online. In this case, our delta H for CO2, formation for CO2 is going to be equal to negative 394 kilojoules per mole. And our delta H of formation of water is going to be equal to negative 286 kilojoules So with these values known, the question I now have is, well, what the heck is our delta H of formation of ethanol? So what is delta HF of C2H5OH? And so we're going to actually use Hess's law and break this down into pretty simple components. So what I want to do is find out, where do all these arrows kind of originate from? And I see that they actually start originating from down here. This is the origin. And from here, we have two paths. We can go straight into our product where they all go to, or we can take a little more circuitous path and we go up to ethanol and then over here to our CO2 and H2O. So no matter what, we're ending at carbon dioxide and water. The question is, are we going straight there, or are we going around through ethanol? And for the purpose of Hess's law, it doesn't matter. So if we look back at Hess's law, these two things are the same. So this entire roundabout journey is equal to the short direct journey. So we're just going to go ahead and look at it in that sense. So we're going to start, in this case, with our roundabout journey, which is a combination of our delta H of combustion and our delta H of formation. So knowing that, I can actually set that equal to our shorter path. That is equal to, and our shorter path is given to us as the delta H of formation. So we are using the delta H formation. And what it says right here specifically is that the formation of 2 carbon dioxides plus the formation of 3 waters is going to be the entire delta H that we have to use. So we can just add right here 2 delta H CO2 plus 3 delta H H2O. And with that, all we have to do now is solve by plugging in our various values. So I know that this is what I'm looking for, so I'm just going to subtract the delta H of combustion from both sides, and then I can just write out my whole new formula. Delta H formation is equal to 2, and our CO2 value is right here, minus 394, plus 3 times minus 286, minus a negative 1367. Now, with that all said and done, all I have to do is do the math, and I can find out that our delta H of formation is negative 279 kilojoules mole inverse. All right, with that one solved out, we're going to go ahead and try a more common version of Hess's law. Now, we don't normally get these kind of weird charts. Instead, we get problems that still talk about intermediates. All right, so our more common version of Hess's law involves taking a bunch of equations and putting them together to get the equation that we want. So basically what we see here is that the industrial method currently used to produce butene-2-ol is the hydration of but2-ene. And we see that we have butene plus water, so it's being hydrated to turn into butane-2-ol. Now we have the enthalpy values for the steps that literally go to make this product. And what we're going to try and do is find the way that we can kind of mismatch and rearrange these so that they kind of equal out, almost like doing addition or subtraction with multivariable problems to get certain variables to cancel out. So what I'm going to do is I'm going to take each one at a time. I'm going to start by looking at this top one. I noticed that we have our reactant on the product side. So what I'm going to do is I'm going to rewrite this where our reactant is on the reactant side. C4H8 reacts to form 4C plus 4H2. Now, because I flipped the problem, this actually takes a different amount of energy to produce. So right here, I see that it is 7.1 kilojoules per mole. Now you'll notice that there used to be a negative, but because I flipped the problem, I flipped the sign. Due to Hess's law, we already know that no matter what we do, the change in enthalpy is going to be exactly the same. So now instead of energy being released, we're going to be putting energy in, and this is actually going to be a positive 7.1 kilojoules per mole. Just putting a little divider. Now, on this next problem, I see that C4H10O is our product. It's what we want. We can leave it exactly as is. So I'm going to go ahead and do the same problem for C plus 5H2. And I'm actually going to go ahead and move these over a little bit. Plus 1/2 O2 reacts to form C4H10O. And now I did not change this problem at all, so I'm going to keep the sign as is, 292.8 kilojoules mole. Inverse. Now, actually, for the sake of this and keeping things clean, I'm going to remove the kilojoules per mole inverse. I just kind of want my values and tables to look cleaner. Finally, for the last one thing I noticed in this problem is that I know that I should start with C4H8 and H2O, and I should end with C4H10O. Now, if I follow each of these, that's all on the right side. But our H2O and our C4H8 started on the wrong side, so I'm going to have to flip that one as well. So on this bottom one, I will do 2H2O reacts to form, I'm going to try and keep these arrows in the middle, reacts to form 2H2 plus O2. And I'm almost done with this. This is going to be minus 483.6, but because I flipped it, it is now positive. So we'll notice that I now have my H2O, my C4H8 all on the right side. I've got my product on the right side, but I still have one more thing wrong. You'll notice I have a 2 on this H2O, but I don't have a 2 in front of the H2O I want. So to get rid of that, I'm actually going to go ahead and divide this entire problem by 2, or maybe multiply by 1/2. And so when I go ahead and do that, I'm also going to multiply this by 1/2. So as I multiply that out, I'm going to get H2O reacts to form H2 plus 1/2 O2. So I'm going to go ahead and replace this current one with this new one. Oh, and I should also have my 483. So that's going to be approximately 241.8, if my math is correct. It may not be. And that's still going to be positive. So I'm going to go ahead and actually, for the sake of keeping this semi-neat, I'm going to get rid of our original one. And I'm going to move our new one up. So last thing I have to do is add all these together, make sure things work. Now, this is a lot more fun than you might think. I have 4 carbon on the right and 4 carbon on the left. So we can go ahead and cancel those. Because if we have carbon on the reactant side and carbon on the product side, it's essentially not there. It didn't happen. And in certain reactions that we'll learn later on, we call those spectator ions. This is not exactly a spectator ion. This is what we would call an intermediate. But for the sake of this, I'm just going to kind of leave it as is. We have 4 hydrogens and 1 hydrogen and 5 hydrogens. So those are all going to cancel. And lastly, we have 1/2 O2 and 1/2 O2. So that's going to cancel. And we are left with our wonderful formula, C4H8 plus H2O reacts to form C4H10O. And the last thing is the delta H is just going to be the sum of all these. So our delta H is going to equal minus 43.9 kilojoules per mole. And that's going to be our answer. So we're going to go ahead and do this next one. This next one talks about the bombardier beetle, which can fire a hot toxic mixture of chemicals at its attacker. The mixture contains quinone, C6H4O2, a compound that is formed by the reaction of hydroquinone, C6H4OH2, with hydrogen peroxide, H2O2. And our overall reaction is as given. So this time, I'm going to try and take things a little faster If you don't feel comfortable doing that, write it out, slow it down. But we're going to try and make sure that we have everything balanced in the end. I noticed two things right off the bat. I have water here in the liquid state and hydrogen peroxide here in the aqueous state. And these we're going to be really careful with. The reason is also be easily confused by these. So we want to watch out for them. So the first thing I'm going to do is try and find my hydrogen peroxide, which I have quickly located as right here in this middle one. So I know right off the bat, that's got to be a reactant. So I'm going to flip that one over and I'm going to write it down here with the other ones. H2O2 reacts to form H2 gas plus O2 gas. And I know that my delta H for this one is going to be positive 191.2 kilojoules per mole. All right, so in the sake of not getting confused, I'm going to actually get rid of the original one, so I'm not even looking at it. Get out of here, original formula. All right, so we've replaced it. Now we're going to move on to our next one. Now I notice that right here, this has everything we want, except for this H2. We're going to have to get rid of that. The only other thing I see with H2 is this guy down here, which it's on the opposite side. It's going to balance out just fine. Love that. The other thing I notice is we need to have our liquid water on the right. We have our liquid water on the right. What do you know? Perfect. So all we have to do is now utilize the rest of these ones, but you'll quickly see a problem as well. We're going to look at the coefficients. We have a 1 coefficient, a 1 coefficient. We have no coefficient, we have no coefficient. We have a no coefficient, again, a 1 coefficient, perfect. We have a 2 coefficient. We do not have a 2 coefficient on our water. We're going to need to multiply this whole thing by 2. Oh. So I'm going to go ahead and just put a 2 in there. This is going to cross out and just become a 1. This is going to become a 2. And we're going to multiply this amount by 2. So our new formula can start to cancel out. And let's go ahead and do it. Let's start off with H2. We have 1 H2 on the right, 2 H2 on the right. So this one and this one are going to cancel out with this one. So I'll go ahead and cancel these. We have 1 oxygen here, 1 oxygen here. So I'm going to go ahead and cancel these. We have 1 water in the gaseous state, 1 water in the gaseous state. So I'm going to go ahead and cancel these. And I'm left with, when I add all this up, my entirely new formula of the one that's shown above. C6H4OH plus H2O reacts to form C6H4O2 plus 2H2O. And then when I add all these up by just doing a quick little sum, I get delta H equals negative 161.8. Hopefully this helps. I'm going to go ahead and put this one right here. I want you to solve it on your own. And when you want the answer, just look later down in this, and I'm going to put the answer right here in this space below. So go ahead, pause it, try and solve this one on your own. All right, if you paused it, then you should be able to see the answer, which is delta H is going to be equal to 96 kilojoules per mole. Much like the first one we did, all we have to do is just look at the ones, see where they end up. I know this has to be in the reactants, not the product, so I'm going to flip the whole equation and make that a positive. I know that should be over in the products. I know that should be over in the products. So the other two are good. Then I just have to sum these out. This 4, once flipped, will cancel with this 4. This 5, once flipped, will cancel with this 4 and this H. This 1/2 O2 will cancel with that 1/2 O2 once it's flipped, and you end up with your 3 separate reactants and products, and you get that total final value of 96 kilojoules per mole. Hopefully this helped. Have a great night.